All right, so when we have to prove statements like this, right, where the sum of all odd numbers is this, the sum of the first, however many positive integers is this, or such and such is always divisible by this. When you get into, number theory, then this process of mathematical induction really, really becomes helpful. So, there are 3 steps, and every single time you're going to follow these 3 steps. The first step is show that it works for n equals 1. So in your series, if n equals 1, show that it works. Second one is assume that it works for some random case. Okay? So if somebody is telling you the sum of the first n positive numbers is this, you go, okay, I'll just hang with you for a minute. Let's just say that what you're saying is true for the first 37 numbers, or for the first, 54 numbers, or for the first k numbers. So you assume that that's true. And then the next step really is key. Then you show that it works for the case immediately following when n equals k plus 1. So if you assume that it's true for 37 numbers, and it holds true for 38, then you know that you've proved it. Now, the proof of the proof is something beyond the scope of the course, so we're not going to go into why that works. Okay, the first thing we're going to prove is this one. And if you look closely at this, this says the sum of the first odd integers, the sum of the odd integers, is n squared. Okay? So, let's just explore for a minute. Suppose n is equal to 5. What does that mean? How many terms are you adding up? You're adding up 5 terms. So it's 1 plus 3 plus 5 plus 7 plus 9. The theorem is telling you that it's supposed to equal n squared. What was n? 5. 5 squared. Now, if you add up all these numbers individually, do they add up to 25? Yeah. They sure do. So let's try it for another one. N equals 7. It's going to be 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. If you add all those up, what should it equal? 49, 7 squared. If you add these up, does it equal 49? It sure does. Okay? So if you take a look at this, what is the last number in the series always? Well, here it's 9, here it's 13. How is it related to your n? It's always 2 times this minus 1. 2 times this minus 1. So that's what this says. That you start with 1 and then 3 and then 5. And the last number is always whatever your n is times 2 minus 1. Okay? So that's what this is. Okay. So let's prove this one. Okay, so here's the proof. You start with n equals 1. If n equals 1, how many numbers do I have on my list? 1. And that number is just 1. Is this equal to now n squared, 1 squared? Is it? Yeah. So, okay, so that step is done because it holds true when n equals 1. Now, assume that it holds true for n equals k. All right? So you go, all right. Let's just assume that you have k of these numbers. What would this say then? Well, you have 1 plus 3 plus 5 plus ... plus 2n minus 1. What's n supposed to be now? K. 2k minus 1 is k squared. That's all for that second step. That step is for points only, free points. All you do is replace this, the n in that, with k. That's it. Minimal thinking involved. Okay? Yeah. In this particular statement, each one that you're going to prove looks completely different. Yeah.
One doesn't work, does it? It doesn't work.
Doesn't? What's 1 squared?
3 plus 5 plus
but if n equals 1, Stephen, then you only have one number in the list. Just the one. Okay? All right. Now, what about the case for n equals k plus 1? So, let's just explore a little bit more. Suppose n is equal to 10, right? What does the series look like? 1 plus 3 plus 5 plus ... What's the last number? 2 times 10 minus 1? 19. And that's supposed to equal what? 100, 10 squared. Now, what if n equals 11? Then 1 plus 3 plus 5 plus ... plus 19, right? If n equals 11, then I'm going to take the list that I had before and add in how many more numbers? One more number, right? Because here n equals 10, I have 10 numbers. Here n equals 11, I got one more. So what's the next one? 21. And now, what is the result supposed to equal? 11 squared. So now, if we think in terms of k, if we call 10 k, then here I have k squared, right? Right? Now, if 10 is equal to k, how can I represent 11 in terms of k? K plus 1. Well, then how would I represent 11 squared? K plus 1 squared. Okay? So, this is what I want. Now, we're going to see if the k plus 1 ends up as that. Here's how we do this. For the n equals k plus 1, you know what? So what I did here doesn't really have anything to do with the proof formally. This is just me exploring, thinking out loud. Okay? Okay, so from here we go to the k plus 1 step. What I'm going to do is I'm going to take this to k minus 1. This equals to k squared. Have I done anything? I just copied it over. Okay? So, this had k numbers. This has k plus 1 numbers. That means in the back of this, I'm going to add one more term. Well, what's the term that I'm going to add there? Is it k plus 1? What's the last term always? 2 times, he hit it right there. What is it? 2 times k plus 1 minus 1. I don't have enough room. Okay? Okay, so all I added is that last term. Now, this is an equation. Can I just add something to one side of the equation and not add it to the other side? No. So whatever I added here, I have to add to this side. Now, I said that the left side of the equation, the right side of the equation has to equal k plus 1 squared. Well, let's just see if it does. This is equal to k squared plus 2k plus 2 minus 1. This is equal to k squared plus 2k plus 1. This is equal to what? K plus 1 squared. Huh? Because remember the last term is always 2n minus 1. N here is k plus 1. Here, n is k plus 1. So it's 2 times k plus 1 minus 1. Now, you have to write, technically, like you have to copy this step every single time. But,
all the way.
Yeah, all the way. But you know what? I'll be nice and I'll let you just do it in the last step. Okay? So there we go. QED. You don't have to write that, but there we go. We proved it. So QED is Latin. Now the next one is the sum of the even numbers. All right? And this says that the sum of all the even numbers is equal to n squared plus n. So if you had like 100 even numbers, 2, 4, 6, blah, 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 100 of them, it would equal 100 squared plus 100. Okay? And we're going to prove it. Okay? So let's start with n equals 1. N equals 1 says if n equals 1, I only have one term. Just 2. Now, is this equal to 1 squared plus 1? Yes, right? So that works. Now, n equals k says 2 plus 4 plus 6 plus blah, blah, blah plus 2k is equal to k squared plus k. So you assume that that's true. Now, is the case for k plus 1 squared? Is the case for k plus 1 true? So if n equals k plus 1, what should the right side equal? Do you know how they say, what's the shorthand for right-hand side of the equation? It's RHS. That means right-hand side of the equation. Or LHS, left-hand side of the equation. So the right-hand side of the equation should equal, what should it equal? If n equals k plus 1, what should that equal to? Right. Now, let's see if that is what this is going to equal. All right, so we're going to do what we did before. I'm going to add an additional term to my list here. So for n equals k plus 1, 2 plus 4 plus 6 plus ... plus 2k. And on this side, I have k squared plus k. Now, when n equals, n, this last term in the list is 2n. When n equals k, the last term in the list is 2k. When n equals k plus 1, what would that last term be? 2 times k plus 1. Okay? Whatever I add here, I must also add here. Is that true? Now, let's see if this right-hand side is going to end up being equal to that. Okay? Well, let's see. There's a cool little trick here that I love. So again, technically you're supposed to write like the left-hand side each and every single time. But I'll let you not, we don't have to waste that much lead. Okay, so here we have k squared plus k plus I distribute this and I get that. Yes? Now, what's that last term? What's that last number there? 2. Is there anything against me writing that 2, not as 2, but 1 plus 1? I can totally do that, right? Why would I do that? You'll see. But let's just write that as 1 plus 1. So now I have k squared plus k plus 2k plus 1 plus 1. Now, look at what I'm going to do. K squared, I'm just going to reorder some stuff. K squared plus 2k, and let's take one of these ones. Plus, what do I have left? K plus 1. What does this factor to? Squared plus? What did I want to get? Okay, like, you can't say this is not cool.
That is very high.
Okay? This is kind of cool. So this...
You factor it to k plus 1 times k plus 2.
Times?
No, you slowly.
You can.
That's another version.
Does that also work?
K plus 1 times k plus 2?
Yeah, because, like, from here, It could be k squared plus 3k plus 2.
Right, but
and then
that's
you can
not
factor
what we
it out.
want. You can do that, but that's not what we want to get.
Would it work?
No, because that's not what we want to get here. I mean, mathematically, it's the factored form of that, but it's not necessarily what we want. So you're not proving that, you're just factoring, but you're not proving the statement that way. All right? So that's one type of statement. Another type of statement are these divisibility statements. So look at this one. It says, prove 6 to the n minus 1 is divisible by 5. Let's just try this for a minute. If n is equal to 1, 6, 1 plus 1 gives you what? 6 to the 1 minus 1 gives you what? 5. Is that divisible by 5?
Yes.
Yeah? What about 6 to the 2 minus 5? Minus 1, I mean. What is that? What about 6 to the 3 minus 5? Minus 1.
Wait, what's 225? Wait, what's 36 times 6? Yeah.
Is it 225?
It's 226 minus 1.
I think it is 225. So, so here are 3 numbers that are divisible by 5. What's another number that's divisible by 5?
6 to
Oh,
1 half.
215?
Wait, can you fraction it? Would it still work?
No. For positive integers n, right?
Yeah.
6 to the 4 minus 1 is 1200.
That works too. So what's another, 10 is another number divisible by 5.
It has to be either 0 or it has to end
Right,
with
but-
0 or 5.
So all numbers that are divisible by 5 are essentially multiples of 5, right? So all of these are multiples of 5. That means you can write them as 5 times some number. Okay? Like this is 5 times 1, this is 5 times 7, and so on. Okay, so enough exploring. Let's just prove this one. For the n equals 1 case, 6 to the 1 minus 1 is divisible by 5. Right? So the one that I've highlighted, that's the statement that you're proving. So you have to write the whole thing. Now, is this true? Is 6 to the 1 minus 1 divisible by 5? Yes, so that works. So now, assume that it's true for n equals k. Well, that would mean that 6 to the k minus 1 is divisible by 5. Okay. So this is fine in English. Mathematically, how could we represent that same statement? Well, I could say 6 to the k minus 1 is equal to 5r. 5 times some number. That means it's divisible by 5, whatever r is. Make sure you don't use k or n, though, for that. Like, right? That's why I chose r. Now,
It could be any other
anything. It could be 5a, 5x, 5p, whatever. All right? So, now, for the n equals k plus 1 case, you sort of have to build up to it. So, here is what we're going to do. We're going to rearrange this and solve it for 6k, 6 to the power of k. So, it's 5r plus 1, right? Now, you do this every single time. Here's what we're going to do. Yeah, we're building up to k plus 1. Whatever the base is here, you multiply both sides by that base. 6, 6. Okay, so now, what does this give you? What's the exponent of the red 6? 1. That means this is 6 to the power of what? K plus 1. When you multiply bases, you add exponents, right? And this is your n equals k plus 1 case now. Right? This is equal to 30r plus 6. No. But now, this is all fine. Okay, I got k plus 1, but how does my statement look that I have to prove? It's 6 to the something minus 1. So now I have to make this look like that. How can I do that? Well, I just subtract 1 from both sides. So I get 6 to the k plus 1 minus 1 is equal to 30r plus 5. Yes? Now, look at this. We're done. 6 to the k plus 1 minus 1 is equal to, can I factor out a 5? 6r plus 1. Look at that. This is equal to 5 times a number. So this is divisible by 5. You see that? So there we go. We're done.
Wait, anything times 5 makes it positive.
No, it's 5 times any number because
This is so cool. I love these. All right. I'm going to stop here today. Your homework for Friday are these.
5.
Yeah. Okay.
You laugh now, but all the longest questions. Yeah.
So now,
It's gonna take us like 2 pages to do.
on Friday, no matter how many people are in class, on Friday,
Oh yeah, it's 11:22. Sorry.
on Friday, I'm going to finish this lesson. Whether there are 1 or 2 or 5 people in class, I will make a screencast. Okay,